Hey, thank you, Stefania, and thank you, all of you, for being here in this last session of the morning. So, my name is Gianni Barlacchi. I'm from University of Trento and Fondazione Bruno Kessler, and today I will talk about the usage of location data to understand cities and how we can use location data for detecting events that are going on in a city, but also to characterize the urban spaces that we have around. In some way, is a kind of a second talk, is a continuation of the talk of before of Michele. So we saw how we can deal with location data, and now let's see how we can use location data. So between the 100 of definition of location data, this is the one that I more like, is the location data is a data located on the surface of the Earth and is characterized by a specific latitude and longitude, or in some way are 2 points that are that are on the Earth according to a specific coordinate reference system. The most used one and the well-known is latitude and longitude. Let me start introducing some of the most popular location data that you can find on the web. And the first one, of course, is Twitter. On Twitter, we can have an explicit location in the text. So we have, this is a Twitter profile from a food trucks in New York, and they are telling to the user where they are, and they attach it to the tweet a location, which in this case is Manhattan. So using the API of Foursquare of Twitter, we can take the latitude and longitude that Twitter associate to Manhattan. So in this case, we have a general idea of the location, but of course, the latitude and longitude can be more specific. This depends on the user. Then we also can have implicit information on the text, and here the challenge is bigger, because we need to understand from the text what are the words related to the location, and sometimes it's not enough, because for instance here we have West Street, Manhattan, but we need to contextualize these two location, and we can do it, for instance, adding information that we have in the Twitter profile of the user that wrote the tweet. So in this case, we know that they are from New York, and so we have New York plus Manhattan, and now maybe we are able to understand that Manhattan is Manhattan in New York. Another very popular source of location data are location-based social network data. So here there is also OpenStreetMap and Google Places that are not really social network, but are a good provider of location data as well. And here we are talking about point of interest. So a point of interest is a collection of information regarding the venue. So we can have, for instance, a restaurant, a police department, and we can find, together with this point of interest, the description, the comments that the user wrote, the picture that the user did in this place, and so on. So using the data attached to the latitude and longitude of this place, we are able to understand what people really do when they go in a such place. And for instance, in this talk, I will use data from Foursquare, but still there are also other location-based social networks that provide more or less the same information. Then another good source of data, which is not available usually, is the mobile phone data. So telco companies, they record for billing purposes our activities. So and it's called call detail records. So in a call detail records, we have information about how, when, from where, and with whom we are communicating. And this information is, of course, geolocalized. It's not our real position, it's the position of the antenna that we use, but in a city center, the distribution of antenna is quite good, so the error on our position is not so high. So we can rely on mobile phone data, for instance, to understand the mobility of people around the city, or to understand how many people we have in a certain area. This is a data set we released together with Telecom Italia, where, for instance, you can find mobile phone data aggregated by antenna in the city of Milan and the province of Trentino. And this smaller and clean version of the dataset described in the paper is also on Kaggle, and it can be, you can just download and play with this data. And for instance, what we have is that we have the cell ID of the antenna, and in another file associated to the cell ID, we have the latitude and longitude of the antenna, and then we have the activities, the different activities that people did in a certain data time with this, on this cell ID antenna. And here, for instance, we kept 3 different antennas in the city of Milan. One is from the area of Duomo, another one is from the area of Bocconi, and another one is from Navigli. And with this just simple plot, we can see that in Navigli, in the x-axis, we have weekly hours, so 168 hours, which is 1 week. And we can see, for instance, that Navigli is clearly a nightlife area of Milan, while Duomo, we have peaks more or less in the afternoon. And Bocconi is a place mostly where people go for the university. So the first 2 days are the weekend, and we have less people. Another data that we can use that is geolocalized is the GPS traces. Also thanks to the growing availability of this of the mobile phone, many applications are able to track our movements. Like an example is Strava, that track our running or training activities. And we can define a mobility trace as a sequence of places visited by a user in a given period of time. And each place can be characterized by like an ID, an arrival time, a departure time, and a pair of latitude and longitude, so the coordinate of this place. And roughly speaking, this is an example. So we have our trajectory that can be projected in the space, and we have the movements in time of the user. Still, this is another data set that is not so easy to find, because, of course, location data are very powerful in the sense that can help us to understand the society, what we have around, but from a privacy point of view, working with location data can be very dangerous. We always have to pay attention. Okay, so we saw some location data that we can find around, and now let's see what kind of application we can do with location data. And this is a short review of this tutorial, this good tutorial that you can find on the web, where they go more in detail with the theory part of the model. Here I will just review some potential application. And the first one is event detection and forecasting. So can we detect and forecast a usual spatiotemporal event? And before thinking how we can detect and forecast, we have to think about what is an event. Because for me, an event could be, for instance, the presence of 100 people around an area at a given time. For a telco company, for instance, an unusual event could be, I don't know, 3,000 of people using the same antenna at the same time. So the definition of event, it really depends on the case, but in general, we can think that an event is an unusual activity that happens in an area, has a specific duration, and engage a certain number of participants. A task, in this case, could be that we input a continuous geotagged social media stream, like tweets. For instance, we can plug all the tweets that are from the Grand Hotel Mediterraneo, and we can try to detect all the events that are happening there. So a good model, in our case, should be able to detect that here, in these days, there is going on a conference. And maybe if the algorithm is even more good, could be also able to detect that this is a tech conference. So this is a reference of a really nice paper from KDD 2017, when they propose a model that is able to perform this task. As we saw the mobility data, so what we can do is actually modeling the mobility with traces, and in this case, what we want to do is to predict what will be the next location of the user. This is useful, for instance, to plan roadworks and understand how people are moving in the city, but also to predict the traffic and estimate the arrival time in a given location. And in this case, we can use the mobility history of our user, and we can try to predict what will be the next location where my user will go. And as for many tasks now, deep learning is outperforming all the previous model, and this is a paper that talks about sequence model to predict the next location. The last application I want to talk about is location recommendation. So we want to suggest to our user nice places that we want to recommend unvisited locations, so places in which our user didn't go, and to do it, we can try to use the collection of previous visited places from our user. And in this work, for instance, they use the check-ins from Foursquare to understand the location that user visited, and they try to infer what are possible places, possible good places to recommend to our user. Okay, now that we saw the application and the data, we can try to see from a practical point of view how we can deal and how we can implement something that use location data to solve a real problem. And we start from the reality. So we have a problem. And in our case, the problem is to classify the land use. Land use classification is usually made with survey, and it's really costly because city municipalities have to analyze all of these surveys, and the collection of surveys is usually done like every 3 or 4 years. And what they do, they divide the city in small areas, like the one that we saw before, for instance, census tract, and they assign to each area a label that indicates the main usage of that area. That could be residential, could be business, commercial, depends on the city municipality. And this approach with survey does not reveal changes in time. So in 5 years, a city like Florence, 5 years ago, was totally different or very different from now. So with these surveys, they are not able to keep track of changes in city. And so we can think maybe about the usage of location data to solve this problem. And now that we define the problem, we have to assess the situation. So, okay, I want to use location data. What are the risks, the benefit, the privacy aspect that I have to take, I have to consider, and also the resource and requirements that we have. And in this case, we need to understand what are the data sets, basically, that we want to use to solve this problem. And our final goal should be a classifier that is able to classify the most predominant usage of an area. And we will see in a bit what means most predominant usage. So the land use data are in Europe. There is this Urban Atlas project from European Commission where they have more than 300 cities divided in small areas, and in each area we have a specific label according to a set of labels that they defined, like high density urban fabric, which means more or less residential, industrial, forest, and so on. So our goal will be, okay, let's try to do it automatically instead of using survey. And the problem, like the one I presented now, is a little bit difficult because the areas defined are very small, so we cannot really understand from location data what we have in 10 square meters. So we can simplify the problem, and we can create a grid over the space and divide the space in small squared cells and try to predict which is the most predominant land use in those cells. So we have these cells, for instance, in the center, which is the red one, that say us, okay, the most predominant land use that we have here is residential. And we try to train a model to do this multi-class classification problem. We need to preprocess the data because data are usually messy, very dirty, and after the collection part, we have to do a strong preprocessing part, like we do more or less with everything, because datasets are usually not ready to use. And at the end, we need to understand if our initial assumption on the usage of location data is reasonable or not. So let's start using Foursquare. We want to use Foursquare to characterize each area of the city. And here we have a geodata frame. Geodata frame, as Michele presented in the talk before, is an extension of a data frame from Pandas where we have this additional column that is the geometry that allow us to work with geospatial data. So we can work with this point data structure from Shapley, which is a data structure that is implemented in an efficient way and allow us to do very quickly many geospatial operations. And then we have the category of the point of interest. So we have the first level, which is travel and transportation, and then we have the second level, which is a little bit more in detail and say, okay, this is a boat or ferries, and so on. So this is the data set that we have. And if we plot the distribution in the city of Amsterdam of this point of interest, we have this result, which is, well, I cannot say that the data set is good or not good. It's a reasonable distribution of point of interest in a city because we have a good amount of food places, nightlife spot places. So, I mean, it's something that I could expect from a city center of a big European capital. And what about the land use? So if we plot, for instance, the land use coverage for 4 different cities in Europe, this is what we have. And we can see that the distribution is quite consistent between the different cities because high density urban fabric is always the most present one, and okay, it's fine because it's the class that tell us that we have residential places, then we have transportation, industrial. So, I mean, still, from this distribution, we can think about the usage of land use, this data set, to understand the land use of a city. As I said before, we need to create this grid. So we can get the shape of Amsterdam and create a grid over this shape. The shape can be, we can take the shape using the Python library OSMNX that is a library that does many things, but one useful thing is in this case is that allow us to take the Amsterdam shape from OpenStreetMap. And once we have the shape, we can create the grid over the shape, and at the end we will have many cells identified by an ID, and we can assign to each cell the point of interest that that cell contains. So here we have the first point of interest with latitude and longitude, and if we do what is called in GeoPandas a spatial join, we can assign to each point of interest the cell that contains that point of interest. So at the end, we will have for each cell a collection of points of interest that are contained in the cell itself. Okay, so now we have the data. We saw that everything is fine. We can go to create our model. And well, for text, for instance, it's quite easy to understand how we can characterize the text because in a document we have a list of words, and we can think like to use the meaning of the word to characterize the document. In this case, we have a space where we have point of interest. So keeping in mind that each point of interest is in some way a collection of words because we have the categories of the point of interest that are telling us the kind of activities that we have there, we can think to characterize an urban area using point of interest for Foursquare. And for each point of interest, we have this chain that semantically describe the activity of the single venue. Okay, so we have words, and now we need in some way to create a vector because we want to do classification. So we need a Fisher vector to input to our model. And following a little bit the idea of bag of words from natural language processing, where we count the number of words, occurrences that we have in each document, and we create a vector with the term frequency. Here we can create a vector with the number of activities that we have under each macro category. So in Foursquare, there are 10 macro categories, and for each cell, we can count the number of points of interest under each macro category, and we can obtain this numerical vector that describe the urban area. And once we have this, we can then create our data set with a feature vector and the label associated to the cell. So we have, for the first example, that the land use is commercial, and we have this feature vector that represent the area. And then we go like we can do in every other machine learning problem. So we do train and test split, and we can use, in this case, I just used a logistic regression to keep the thing simple. And we can use the data frame as a metric. So we have our feature vectors, we have our target label, and we train our multi-class classification model. And then we evaluate the model using accuracy, FA1 score, precision, recall, all of these standard metrics. Okay. But using a simple vector that just tells us, okay, you have 10 restaurants there, you have 1 church, is not really informative. And there is this other approach where if we think about this image with the point of interest, we have a collection of chains. If we get all the chains, we group all the chains under a fake root, what we have for the cell is a tree. And we can think to represent our urban area as a tree. And we can use this tree, which contains much more information than that the backup concept vector of before. And we can think to use this tree representation as an input for our machine learning model. So there are machine learning models that can take in input tree structures. And in this case, we can build a tree structure in this way, where we call it this approach geotree. So is a tree where each node corresponds to the Foursquare category, and the ages among the point of interest are the same that we have in the hierarchical tree that is provided by Foursquare. Okay, and it's also nice, this representation, because it allows us to see, to visualize what we have in an area. So we have a square, and this is the tree that characterizes this square. Of course, this is a very simple tree because we have only one level, but we can have even more complicated tree like this one. And what we can do in order to create many features that represent our cell, we can apply some function that basically create many possible sub-tree from the initial one, and we can at the end represent our cell with a set of sub-tree. So in this cell we have this sub-tree, we have this other sub-tree, and so on. So at the end, instead of having only 10 features, we will have many, many, many features that take into account the presence of many different points of interest, single point of interest. Well, once we have all of these substructure, we can even think about, okay, I have a residential area, but what are the most important things that, for instance, in Amsterdam, characterize an urban area? And we can, like, mine the structural patterns that we found dividing our trees. And what we have, for instance, is that in Amsterdam, sport and leisure facilities area are characterized by the presence of this subtree and the presence of athletic and sport and pools together. So this is something more than the simple presence of one restaurant, one church, and so on. And like the same is for the high-density urban fabric that says, okay, a residential area is characterized by the presence of assisted living point of interest and residential building. And then I don't know, but in Amsterdam, in residential area, they also have Indonesian restaurant. And this is another insight that we can take from this analysis, because we run this analysis on different cities in Europe, and for each cities in Europe, we always obtain different substructures. So what characterizes a residential area in Amsterdam is not what characterizes a residential area in Milan or a residential area in Amsterdam. So these sub-3 are telling us many things about what we have in the area. Okay, so now that we know how to characterize, so how to build Fisher vectors, we can test our model. And still, we do the same things that we do for every classification problem, with the difference that here we have a variable, which is the cell size, that affect our analysis. So we have to take in consideration the dimension of the space that we are going to classify and we are going to characterize. And here we run the experiment using different cell size, and I mean, nothing of surprising. Depending on the cell size, we have different results, and is not consistent among cities, because a square of 500 meters in Amsterdam contains different point of interest, and the distribution of the point of interest is different than a cells of 500 meters in Milan or Lisbon. This is because every city is different from each other. The cities are different from each other. To conclude, at the end, we need to deliver something. And if you want to deliver a land use classifier, what we have to do using location data is to map the location, to simplify the approach and create this grid, map all the point of interest that we have onto this grid, and build the Fisher extractor, that in this case is the area tree generator. And together with the tree, we can also add additional features that, for instance, can be the bag of concept vector that we defined before. Because one weak point of the tree is that we are not taking in consideration the frequencies of point of interest. So if I have 2 cafes, in my tree I have only 1 path. So I'm not taking in consideration that I have many different points of interest. I have many times the same point of interest. And to overcome this problem, we can add an additional Fisher vector, which is the simple bag of concept vector that we saw before, that take in consideration the problem of having more point of interest of the same category. Okay, that concludes my talk, and thank you to everybody.
Thank you, Gianni. Do you have any questions? Yes?
Congratulations, very interesting talk. Are you planning to use these results for commercial use, for example, building an app, stuff like that? In general, is there a demand for such city classifications in the market from someone?
Yeah, so one weak point of this approach is that we are not taking into consideration temporal activities that we have. So the results that we have are not, in my opinion, enough good to think about commercialize this approach, because we should also take in consideration how many people we have, what is the time activities of people that we have in the city. So from using only location data from Foursquare, we are only considering the activities from a commercial point of view, let's say. So is a static representation of the area. So we should add more information. There is a demand. I don't know. I mean, I don't know any product that are now substituting the standard survey, but it's something that, in my opinion, could help a lot the city municipality, because they collect this information every 5 years, and now the cities are changing a lot even in 1 year. So it's something that is very important to keep track of the changing in the city.
For example, an usage of this is I don't know, for a consultancy company that does advisory on for third parties for building economic activities in a city, you might spot areas that are not well, let's say, if there's not enough supply of cafes, for example, and so this company might use your data to suggest third parties, hey, there's a demand of cafes down there, you're probably setting up a successful business because there is a supply and demand problem. It's just an example.
No, yeah, absolutely.
I see a lot of applications just from these few slides you presented.
No, I mean, I agree with you. This is, I was answering to your question, taking in consideration the task of land use classification. Of course, this representation of urban areas can be applied to many different tasks. I mean, all the tasks where you need to characterize the urban areas can use this approach. So like, you want to know if a business will be successful or not in a place, you need to characterize the area, and this could be an approach that can help, for instance, a company to decide if open or not a shop there. Yeah.
First of all, thanks for your presentation. As I see, the Geo3 is like a fixed taxonomy, and I would like to know if you could take a consideration of using ontological structure for inferring a new taxonomy, for example.
Okay, so these are the Geo3 are built using the taxonomy that we have from the point of interest provider. So in the case of Foursquare, they have their own taxonomy, which is a very nice taxonomy, and we use that taxonomy to build the Geo3. We also tried with OpenStreetMap, but with OpenStreetMap, there isn't a clear hierarchical representation of point of interest. So we try to build our own taxonomy, but well, I don't know if we will succeed. At the moment, we are not obtaining the same results as Foursquare. But using OpenStreetMap, for instance, could be a very nice achievement, because in OpenStreetMap we have free open data, while in Foursquare they are basing their business is based on providing this data. So it's not easy to obtain data from Foursquare, at least in a quickly. Okay.
Other questions? Okay, so thank you again.
Thank you.
And